Are you still turning on your lights with one of these old-fashioned light switches? Well, to get with the times, I bought some of these smart light bulbs for my house. Unfortunately though, these aren't actually all that smart, and you need to use something like an app or a voice assistant to turn them on, so it's never been more complicated to turn on my lights. I think most reasonable people in my position would go to Amazon and buy one of these smart buttons or proximity sensors, but where's the fun in that? So instead I'm going to be building my own DIY smart buttons from scratch. Later I can stick these to my wall and use them in place of my old switches. Though if you wanted to, you could make this button trigger any other type of home automation script you can think of. While I'm at it, I'm also going to show you how, with some small tweaks, this button can transform to solve most of my other smart home sensing needs. And hidden inside each of these boxes is a single coin cell battery that should last up to 5 years before you need to replace it. As always with my videos, all the code and final electronics in this video are custom designed, so we aren't going to be using any Home Assistant, ESP32, Wi-Fi, Zigbee, Bluetooth, or any other existing stuff like that. So buckle in for the most exciting, boring video about buttons you've probably seen in a while. So the general plan is that I'm going to have some microcontroller that will act as the brains of the button. This will be connected to the button and optionally other sensors that are useful for home automation. I don't want to have to run wires from my lights to my buttons, so the microcontroller is also going to have some wireless radio that will send out data packets whenever the button or sensors are triggered. To receive this data, I'm for now going to have another radio connected to a computer that will in turn be connected to my regular home automation stuff like lights over my home network. Also, since we're going wireless, we're going to need to have a battery connected to everything on the button board to power it. I don't want to worry about this thing for a while, so the goal is for this battery to last at least a few years before it needs to be replaced. What this implies is that everything on my button board needs to be as low power as possible. Anyway, to start off, I need to pick a microcontroller to use. Nowadays, there are a lot of options ranging from Arduinos, ESP32s, STM32s, Raspberry Pis, and so on. Probably the most important difference between these for this project is the power consumption. As a point of reference, I have a Raspberry Pi 5 here, which is a pretty standard single board computer nowadays. If I plug this thing into power through a USB power meter, it consumes a bunch of extra power during boot, but will eventually stabilize to around half an amp of power draw. Even if you power this from a big USB power bank like this one, the Raspberry Pi will drain the whole power bank in around half a day doing light tasks. In comparison, Raspberry Pi also makes these Pico microcontrollers. I have a basic program on it right now for blinking an LED, and it consumes way less power than the full-blown Raspberry Pi if you don't need a lot of computation power. Measuring the USB power draw isn't particularly fair though, since the power has to flow through these diodes and converters that you see on most microcontroller boards before the power is low enough of a voltage to feed to the microcontroller chip. Not all of these are needed if our board is battery powered, and any extra unnecessary components left over will end up being dead weight that just consumes more power. To get more precise raw measurements, I'm going to be switching to directly plugging in the board under test into this power profile tool. This thing plugs into my computer via USB so I can log power measurements directly to my computer. Note that at least on this board, you can't fully bypass the conversion circuitry, but we should still be able to get a rough idea of the raw power usage of just the core chips. The code that I'm currently running on the microcontroller looks like this and just flips the LED on, waits 1 second, turns it off, waits another second, and then repeats the whole process forever. And if you record the power usage over time, it uses on average 22 milliamps with the LED on and around 14 milliamps with the LED off. Just note that I'm calculating average current draw since the current graph is super noisy over time due to how the DC to DC converter that we didn't skip works internally. Anyway, depending on what you're doing, 14 milliamps can be pretty good, but at least for this project this is pretty bad. The Pico is a fairly high performance microcontroller with a lot more power than we need for this project. So I also tried vibe coding a bunch more code to lower the clock frequency and turn off all the features we don't need to reduce the power usage further. None of the code is super important, but the best result I got was around 1 milliamp at 3 volts with most of the optimizations you can do. If you've watched any of my other videos, you can probably guess that we're not going to be using a Pico microcontroller. Instead, we're going to be using an nRF52, which comes in a lot of form factors like this USB dongle. Most likely you already have one of these in your home, since if you have a wireless mouse or keyboard like this, then most likely there was probably one of these chips inside of it. The nice thing about these is that they also have a built-in wireless radio, but the downside is that it has much less CPU performance than the Pico. Though in my opinion this is still good enough for 99% of projects, and if you've watched my previous videos, it's even good enough to power a 3D printer. Anyway, where this thing really shines though is in power consumption. Running the same LED blink test on this board shows that we can get down to around 2.6 microamps, which is hundreds of times lower than what we can get on the Pico. You can also see from this graph that the LED now takes hundreds of times more power to run than the CPU, so we're now at the scale where things that you traditionally consider to be low power are not. Note that you don't strictly need to measure the power usage when designing a board, since the nRF52 datasheet is very detailed when it comes to documenting how much power the chip is supposed to consume in different modes. But just be aware that if you try to reproduce these numbers, you'll probably fail on the first try, since this requires a bunch of software flags configured correctly. The current mode that I'm using is roughly the same as this mode in the table here, and we are getting roughly the same expected current consumption. Also, what's kind of interesting is that if you look at the row above this one, you should be able to cut your power consumption by half if you turn off all the RAM. The RAM on microcontrollers is fairly similar to the RAM in your computer and needs to be continuously powered to store any data. So intuitively, it makes sense that we would use less power if we had less RAM. The specific chip I'm using has 256 kilobytes of RAM. If you're watching this in 2026, you'd probably think I'm rich for being able to afford 256 kilobytes of RAM in this economy. Just like graphics cards, a lot of microcontrollers like the one I'm using come in a lot of different variations with different feature sets. Right now I'm using the top of the line version, which costs around $6 per chip. If you were an engineer at a company trying to make this into a real product, you'd likely want to buy one of the lower end versions like this one, which only costs around $2 in bulk. Though luckily for me, the NRF chips have a feature that lets you turn off the RAM in software. I don't need most of the RAM for this project, so I'm going to reflash the chip to turn off all but 32 kilobytes of RAM. And if you remeasure the power consumption again, we get down to around 1.4 microamps of current. I still haven't explained yet how blinking an LED has anything to do with making a smart button. To make what's going on more clear, I'm going to reprogram the microcontroller to just keep the LED always off, but still wait 1 second between pulses. In this case, if you record the power usage, it looks like this. You can see that for most of the time, our power usage is on average around the 1 microamp level we measured earlier, but every 1 second, there is a spike in power usage, which is the CPU waking up from sleep since the 1 second timer elapsed and the CPU needs to figure out what to do next. If we still had the LED code, this would be when it flips the pin to turn the LED on or off. Conceptually, what the code is doing is the following. For simplicity, let's assume that we start with a step that sleeps for 1 second. In the sleep function, the code will set up a timer for 1 second in the future. And also inside of the sleep function, it'll run the special WFI instruction for ARM processors. This is an actual instruction for ARM processors which waits for interrupts to occur. You can think of interrupts as interesting events in time, like when the timer finishes counting down to 0. While it's waiting, the instruction will put the CPU to sleep, so will consume very little power. After the timer interrupt eventually triggers, the CPU will wake up and then the code to flip the LED on or off will run. Then the whole process will repeat itself forever. Another way to think about this is like closing the lid on a laptop. When you do that, your computer will turn off the display, go to sleep, and try to conserve power. And then when you open the lid back up, a sensor in the lid will interrupt the CPU, which will rush to turn everything back on. In the context of making a wireless button, the code will follow a fairly similar pattern. First, instead of setting up a timer, we will set up a button watcher, which will monitor for when the button is pressed. Then we run WFI as before. We aren't going to be getting button presses all that frequently, so for over 99% of the time, the CPU will be sitting in this state and consuming very little power like we saw before. Once the button is pressed, the waiter will wake up our CPU, and then we will send out the notification to our computer to tell it that the button was pressed. Then this whole process will repeat itself for the next button press. The main constraint we have when implementing something like this is that the box waiting for the button needs to be some electrical signal that our microcontroller supports and understands how to react to. From an electrical perspective, buttons are usually set up like this. We'll have some red power wire connected to one side of a resistor and the other side connected to the switch. Our microcontroller is going to be monitoring the voltage on the bottom side of this resistor. My microcontroller is currently on vacation, so this multimeter will be taking its place. And you can see that it is initially sensing a high reading of 3 volts. When the button is pressed, the button will make a connection to the ground wire of our power supply. Since there is no resistor on this side, the main resistor is effectively overwhelmed and the signal becomes low, close to 0 volts. These sharp high to low transitions are luckily something that basically every microcontroller can monitor via GPIO interrupts and takes close to 0 extra power to set up. Coming back to my microcontroller dev board, the one I'm using already comes with a button installed. So I made a quick program that flashes the LED for half a second when I press it to simulate a radio packet being sent. If you try recording the power usage during a press, you'd get something like this. Initially, the power usage is still very low since we're waiting for the button press. Then when the button is pressed, the power usage jumps up since the LED is on. But the interesting thing comes after this, since after the LED turns off, I was still holding down the button for a while and the power usage is still relatively high. This is mainly because while the button is pressed down, power is continuously flowing through this resistor to ground. So you really need to be mindful about picking a large resistance value or using internal pull-ups that you can turn off after the button is pressed to avoid consuming extra power before the user lets go of the button. Now we're done optimizing the power consumption for the microcontroller and the button, so now we need to actually set up the wireless communication parts. If you look at existing smart home products on Amazon, you'll usually see a few common wireless protocols flying around. Wi-Fi, Bluetooth, Zigbee, and Z-Wave. These are also all super complicated, and you can tell they were built by large bureaucracies, since if you try reading the Zigbee specification for instance, it's over 500 pages long, and I don't have time to read all of that. On the nRF52, there's a relatively simple radio interface, which basically lets us give it arbitrary data to send as wireless packets. Internally, the microcontroller translates that data into radio waves that can be received by another microcontroller board. Unfortunately, there are a few reasons why all wireless protocols aren't this simple. First, in terms of reliability, you most likely have other electronics around you that will emit their own signals, and if one of them hits your button's data packet, it will get corrupted. The simplest way to solve this is to just send 2 copies of the data. If the first half of the packet is corrupted, the receiver can detect this and do nothing. After a short period of time, the button will try retransmitting its data. If the second packet is received successfully, the receiver will send an acknowledgement packet to the button to let it know that it successfully received the data. This way, the button knows that it can stop trying to retransmit the data. Note that in practice, instead of repeating the data, we'd actually use a CRC checksum, which does the same thing but uses less space. The second set of problems is introduced if we start having multiple buttons. The most obvious change that we need to make is that now when we send a packet, we need to include the ID of the button so we know which button was pressed. If one of the buttons gets pressed shortly after the other, the wireless packets may overlap in time and result in garbage getting received on the other end. This is basically the same scenario as we saw earlier, but if both devices follow the same behavior of immediately retrying, the retry is likely to also get messed up. The solution to this used by Zigbee is to have the devices listen briefly for other ongoing transfers before continuing. So basically, if the first button is pressed slightly before the second one, it'll start transmitting first. The start of the packet will get noticed quickly by the second button, and the second button will shut itself off for a random period of time. Later, the second button will retry once it stops seeing active radio transmissions. This method is good for low amounts of traffic, but will fail frequently at some point, so if you look into protocols like Wi-Fi, they use much more complicated multiplexing methods that also consume a lot more power to implement. The other big issue you need to deal with when going wireless is security. Basically anyone can buy their own microcontroller, so it's possible for a hacker to sit around and monitor your packets since they are readable in plain text. Even worse, the data is predictable, so a hacker could just forge their own packets and mess around with your lights. What we'll need to do to solve this is to use encryption. First, we'll need to preload some secret key onto the button and our receiver. Then when the button has a packet that it needs to send, it'll encrypt it using the secret key before transmitting it. Once the receiver gets the packet, it will decrypt it using its local copy of the secret key. This doesn't entirely solve the problem though, since encryption is deterministic. So a hacker can just wait to receive one of the good encrypted packets, then they can record that packet and replay it later since every button press packet looks the same. To solve this, you'll usually see a counter included in every packet, which starts at 1. When the packet is encrypted, the counter is added to the key, and then that mixture is used to encrypt and send the packet. The next packet will do the same with a counter that is 1 higher than the last one, so it'll result in a different encrypted packet being sent. Meanwhile, on the receiver side, the receiver will keep track of the last counter value received. If the receiver ever receives a packet with a lower counter number, it'll reject it since that would only occur if a hacker is trying to replay an old packet. Since the hacker has never seen a packet with high counter values, they can't predict what the next valid packet will look like. Note that for the counter, we are using a 32-bit integer, so there is a maximum value at which it overflows and has to go back to 0. It is not cryptographically secure to reuse counter values, so once you overflow your counter limit, your device needs to stop working until a new key is agreed upon. Though in practice, the battery is going to die well before that happens. Anyway, the full algorithm we will use is called AES-CCM, which is also used in Bluetooth, Zigbee, and some other places. In short, it's a combination of CBC mode encryption, which is the counter method we just talked about, with a MAC calculation, which is essentially an encrypted version of the checksum to prevent blind tampering. Generally, you should always prefer to use a library like OpenSSL instead of trying to implement any of this yourself, since there are a bunch of traps you need to be aware of to implement these securely that I've skipped over in this video. Anyway, the last important detail that I omitted from this description is how to get the keys preloaded everywhere. Most existing protocols implement a process known as key exchange. At a very basic level, this effectively involves sending a few initial packets back and forth with parts of the key so that eventually both devices have the entire key. But there's also a bunch of math that makes it much more secure than it sounds. This process is way more complicated than the encryption parts, and in case you're curious, this is the part that quantum computers are expected to break if they ever get powerful enough. Most existing protocols like Zigbee are still using traditional algorithms for this, which haven't been upgraded to be safe from quantum computers yet. My solution to this is much simpler. I'm just going to plug in all my boards into my computer via a USB cable and just transfer the secret keys that way. You'll generally see this being called the pre-shared key method. Assuming no one has tampered with your USB cable, this is pretty secure and you don't need to worry about complicated key exchange processes. Just be aware that if anyone has physical access to your device and steals it, it is possible for them to extract the secret keys, though this is possible with basically all encryption methods to some extent. Anyway, coming back to the main project, I still have the dev board wired up to the power monitor and waiting for button press. To act as the receiver, I have a second dev board here attached to my computer via USB. Now when I press the button, you can see the LEDs in the receiver light up, showing that it has received some data. If you try recording the power consumption, you'll get something that looks something like this. The first 10 milliseconds are spent just waiting, since we want to filter out short button presses, which might just be noise due to vibrations. Then we have a high power pulse that lasts for around 1.5 milliseconds and peaks at around 17 milliamps of current. If you zoom into this, you'll see two distinct pulses. The first is the biggest spike, which lasts for around 200 microseconds, which is when the radio transmitted the data packet. If you read up on other wireless protocols, they are usually designed to keep the data packets as small as possible, since smaller data equals less transmission time, which translates to less power usage. The second, slightly smaller pulse after that one lasted around 400 microseconds and is when the radio was trying to receive the acknowledgement packet from the computer. There are two important observations that can be made from this. First, even if we aren't transmitting, we will still consume a bunch of power just listening for packets on the radio. This implies that in order to conserve power, the other device must respond with an acknowledgement as fast as possible to minimize the wait time on any battery-powered devices. In my case, I am cheating a bit, since when the receiver microcontroller gets the packet, it immediately sends out the acknowledgement before it tells the computer. So there is a risk here that if the connection to the computer temporarily breaks, we may miss some data, but that's much less likely. The last major design step for this project is to pick a battery. Nowadays, most electronics like phones, laptops have lithium-ion or polymer batteries like this one. The nice thing about these is that you can recharge them and they hold a lot of energy. The main downside of these is lifespan. For our use case, we're going to be consuming very little power most of the time. And if you look around in LiPo datasheets, they'll generally warn against storing these for longer than 6 months fully charged, since they will deteriorate over time. And if you've watched the news fairly recently, these things have a habit of catching on fire on airplanes, so it's probably not a good idea to be putting too many of these in your home. You'll also sometimes hear some of this characterized as self-discharge, which is the effect of the battery leaking power from just sitting around. Depending on the battery type, this can be several % of loss per month. The other annoying thing about LiPo batteries is that if you measure their output voltage, it'll usually be around 3.7 volts, though you can see this going up to around 4.2 volts. If you look inside the datasheet of most modern ARM microcontrollers, they all only work with voltage levels close to 3 volts, so if you want to use a LiPo battery in your project, you need extra circuitry to step down the voltage to use it safely. So instead, we're going to be using these CR2032 batteries. You'll probably see these used in things like key fobs and AirTags. These are unfortunately not rechargeable, but these are supposed to have effectively no self-discharge or deterioration, so should last several years without problems. And if you measure them, they have a voltage much closer to 3 volts, so most microcontrollers can be directly attached to this battery without extra circuitry. Just know that the voltage isn't constant, and as you discharge the battery, the voltage will slowly go down. This is usually what your phone and laptop measure when they are trying to figure out how much battery percentage is left. Also note that this battery is fully dead around 1.8 volts. According to the datasheet from my microcontroller, the minimum recommended input voltage is around 1.7 volts, so theoretically we should be able to use all the power in the battery, but if you are using a different microcontroller, you may not be able to get that low. So that I know when the battery is close to dying and needs to be replaced, I'm going to have the button wake up every minute and sound out a ping packet with the current battery level. But there is one more annoying caveat that makes this voltage over time graph incorrect. To demonstrate this, I made this test board that will let me measure the voltage of the battery and also drain it with the dummy load. The dummy load is attached through the blue wire to my pulse generator, which will turn on the load for 2 milliseconds at a time. The other wires are attached to my oscilloscope, which will allow us to see the battery voltage over time. The yellow line is the output from the pulse generator, which is still a flat line since I haven't turned it on yet. And the purple line is the battery voltage. When I trigger the load to turn on once, here's what happens. As you can see, the voltage drops very sharply, down by 0.1 volts in this case. You can think of this as being what happens when we press our button, since we suddenly go from consuming very little power to consuming a lot of power. The issue with this is that if we pull too much power, the voltage may drop below the minimum that our microcontroller needs for running, so the microcontroller may crash. The main cause of this is the internal series resistance of the battery and is usually in the tens of ohms for these batteries. The solution to this is fairly simple and just involves adding one of these capacitors in parallel to the battery. These effectively act as a fast responding power bank. If you look at most modern electronics, you usually see a ton of capacitors everywhere for a similar reason, though technically the reasoning for those is usually high source impedance and not just DC resistance like with batteries. The main downside is that the one I'm using consumes around 1 microamp of extra power continuously due to leakage. Anyway, if you set everything back up and test again with the oscilloscope, you'll see something like this. Here's also the old result for comparison. We still end up dropping the full way eventually, but you can see at the start of the drop is now much more gradual, so this should help to absorb some of the larger spikes in power draw. The other important number you will see on batteries is the capacity, which is usually around 220 mAh for CR2032 batteries. This basically just means that you can draw 220 mA of current from the battery for 1 hour before it dies. You can also scale this, so it means that you can draw 110 mA for 2 hours and so on. Our current consumption with the capacitor factored in is around 2.4 microamps while sleeping. We also minimally wake up for 2 milliseconds every minute to send a battery status update which consumes around 5 milliamps, which if you do the math is on average 0.17 microamps. So total continuous power consumption is on average roughly 2.6 microamps. So 220 milliamps divided by 2.6 microamps is roughly 9 years of battery life. This will vary a bit if we add other sensors to the board. Also, some of the components will age over time, so I don't think we'll make it to a full 9 years of battery life, so don't forget to subscribe for the next status update in 5 years. Okay, so this video has been going for 20 minutes so far and we haven't actually made anything yet. Well, that changes now, and we're going to make the final product by combining everything we've collected so far. The first step is to design a PCB that puts everything together in KitKat. This is basically the smallest board I can make that fits the battery and also leaves clearance for the antenna, which ideally needs to be as far away as possible from any other metal on the board. And here's the cool 3D preview with most of the components attached. Though when you order this from your favorite PCB manufacturer, the boards will end up looking like this. When you get them, you first need to apply solder paste to hold down all the components. Then we can start laying down the components. For the microcontroller, the traditional approach is to get all the individual components like the main chip, flash, oscillator, antenna, and so on separately. But instead I found these tiny all-in-one modules that make it much easier to make all the electronics really small. And this module just fits onto the pads on the top of the board. Believe it or not, it's really hard to put these down in the right position when filming behind a camera, so bear with me here. Then I'll add the capacitor. And then we can put on the button. Know that the pull-up resistor for the button is inside the microcontroller and controlled through software. Also, I didn't mention earlier, but for USB to work correctly, you also need to add these resistors. If you've watched my other videos, I usually melt the solder in an oven, but since these boards are so small, I couldn't resist using this adorable little hot plate. This will take a few minutes to heat up the board, and probably the coolest moment is right here when the solder melts and the surface tension between the molten metal shifts everything into the right position. The other side of the board follows a similar process with first applying solder paste, but there is really only a programming connector, a USB connector, and a battery holder on this side, so it isn't really that interesting. Once everything is soldered and cleaned up, the board looks like this. I also added a tiny blob of solder on the right side of the jumper right here. This basically configures this to run off battery power. If you solder it to the left side, the board will be powered from the USB cable, so you can use this as a standard USB button. Anyway, this thing is still pretty useless since these microcontrollers come with literally no code pre-installed. So first I'm going to plug in the board into my computer via this ARM programming tool. Then I'm going to run some commands to flash the USB bootloader. Then I can plug in the board via the USB connector, and it shows up as a bootloader in my list of USB devices. Then I can run some more commands to compile the sensor firmware for it, and then I'll flash it to the board. Then the board will restart and show up as a USB device attached to my computer. I'm now going to bring back in another of the USB dev boards I have to act as a receiver. For now it's connected to my computer, but for continuous operation I'm going to switch this board over to running on a Raspberry Pi 24/7 after this video. Anyway, to use the receiver, I'm going to open a second terminal tab and start a bridge program that'll connect to the receiver and let other programs access the receiver on my network. Now coming back to the main tab, I'm going to run another command which does the following three things. First, it'll register the device with the receiver bridge program so that it knows to expect packets from the button. Second, it will send the device's encryption keys to the button board. And third, it will configure the board to act like a button. The third step is basically just sending over a protobuf config file that looks like this to the board. Depending on what you want the board to do, you can change this file. Okay, so the board is now ready, and we can unplug it and insert the battery. Now back on the computer, I'll run another program that will run the pipeline that listens for packets from the receiver and sends them to my Lights API. And now in real life, we can test that the button works by pressing it a bunch. Lastly, to make this thing look a little more polished, I also made this 3D printed case we can put it in. And we can now retest that things are still working, and now we're done. Okay, so it's not the end of the video yet, since I haven't explained what all these other empty spaces on the board are for. Well, when you're manufacturing anything, buying more of the same thing usually ends up being cheaper due to economies of scale. For the PCB manufacturer I'm using, you literally can't even buy less than 5 boards. Also, after browsing all these DIY sensor kits online, there's quite a few that are fairly useful to have around your home. So I ended up packing a bunch of sensors into one board, and then ended up ordering a bunch of these bare PCBs to assemble. In the case that I just need a button, I'll just populate the components for that and save on the component cost for the other stuff. Otherwise, I'll add more components depending on what functionality I want. And if you've followed everything up to this point in the video, you'd be surprised how many other things you can do following the same pattern. Just to summarize, the core premise behind this project is that in order to achieve long battery life, we are only attaching button-like things to our microcontroller. So we are looking for sensors that match two main criteria. First, we want things that consume little to no power most of the time when idle. And second, we want sensors that infrequently send out sharp trigger signals to our microcontroller to wake it up. The first button-like object I added to this board is this accelerometer chip. These are what you have in your phone that allow it to detect which orientation your phone is facing when you tilt it at different angles. For this demo, I'm logging all the sensor data at full speed over USB to my computer, which is useful for initial tuning since once it is battery powered, we won't be able to afford logging data this frequently if we want it to last multiple years. The chip that I'm using can be configured to act as a motion sensor, which basically acts as a button which triggers when the board is moving or vibrating. If you are designing your own board, you want to look out for these interrupt pins in the chip pinout, which are the outputs that send out the trigger signals to your microcontroller. In terms of power consumption, this chip can run in this motion detection mode while consuming only 270 nanoamps, so shouldn't affect our battery life all that much. In terms of what to use this thing for, I stuck one of these to my laundry machine, then I started the machine, and later on, especially during the final spin and rinse cycle, the machine shakes a lot, so we can sense when that ends and send out a notification to my phone that my laundry is done. Then I added a spot for this chip. This is basically a switch that turns on when a magnet is nearby. I have another 3D printed part here that has a magnet on one end. If I move the magnet close to the board, you can see the receiver flashing after a half-second debounce period. And the same thing happens when I move the magnet away. Just note that this thing consumes around 0.5 microamps continuously, so will last a few years less than the rest of my sensors. I've mounted one of these to my front door frame with a magnet opposite it on the door itself so that I can use this to sense when someone walks in to trigger stuff like lights or security cameras. Note that if you Google how to do this, you will usually encounter these reed switches. These internally have two metal strips which move when a magnet is nearby. Since these are mechanical, they are less reliable than the Hall effect sensors we are using, and they will continuously consume power when the door is closed since they will act like a button that is pressed down most of the time. Next, since some sensors are too big to fit on this board, I added these expansion headers on the corners to allow you to directly run wires to a sensor, or you can use them to attach expansion boards. Since all the tiny wires are on the main board, it's much easier to make the expansion boards, and I can even make them at home on my CNC. First expansion board I made is for this passive infrared sensor. And I made a 3D printed case that goes over the expansion board. These are what you normally see in motion sensors, and from an electrical perspective are effectively just buttons. Normally you do something like turn on your lights when it detects motion, and later turn off your lights if motion hasn't been detected for a while. The main thing to keep in mind with these is that the signal isn't as clean as a button. Here I have one of these sensors attached to my oscilloscope, and you can see that as I wave my hand over the sensor, you can see that the output signal sometimes glitches and drops for short periods of time. In your board config, you'd want to configure the debouncing timeout to ignore responding to fast pulses to avoid draining too much battery. The next expansion board is a knob that you can use for things like volume or light dimming. I also made a nice case and knob handle for this. Currently this thing is fairly bulky, though you can make it smaller if you directly solder on the expansion board instead of making it removable. Usually what you'll see used in electronics as knobs and joysticks are potentiometers, like this one. If you wire these up to an oscilloscope and try spinning them, you'll usually see a smooth, linear transition in voltage levels like this. This doesn't match our button-like trigger requirements, and it's a bit annoying to make a microcontroller wake up when this type of analog signal changes. So instead I ended up getting these quadrature encoders. When you wire these up, they require a few more extra components, and it will output two signals, which are the yellow and purple lines on screen. When you spin them, they will generate pulses incrementally as the knob spins. So the resolution of these isn't as good as the classical potentiometer, and you don't know the absolute position of the knob, but they will give you sharp trigger edges, so we can fairly easily make a microcontroller wake up and count the number of pulses it gets. Not everything falls into this button-like pattern though. On the other side of this board, I added this chip which is a temperature and humidity sensor. Changes in temperature and humidity generally don't have very sharp events that we want to be notified about. Like I mentioned earlier, for reporting battery life, the board already wakes up every minute to report the current battery level. So I've set up this sensor to piggyback off of that and collect a single temperature and humidity measurement every minute. I left this thing outside on my patio for a day to collect my outdoor weather. The tiny hole in the case is to let the outdoor air reach the sensor. In case you're curious, here's what the weather looks like outside my home all day. Now I just need to find a reason to go outside. Some other stuff is just way too power hungry to be idling all the time with a battery. On the bottom side of this board, I still had free space, so I added these components which let you connect an e-ink display. You can use this to periodically draw arbitrary text like a daily weather report or reminders. E-ink displays are known for their ability to be completely disconnected from power and still retain their image. The main issue though is that all the driver circuitry still consumes quite a bit of power while doing nothing, even if you put the display into its deepest sleep state. So to solve this, I added a tiny electrical switch right here, which will completely power off everything needed for the display. That way we can support high-powered devices like this display as well, assuming we don't need to use it very frequently. As for how the wireless communication works, as usual, the microcontroller will sleep for a minute, and once the timer lapses, it will send out a status update to the receiver with its current battery level. If there has been a change to data that needs to be displayed, the receiver will send it back as part of the acknowledgement packet. So it does unfortunately take a minute of latency to update the display, though you could reduce this if you want to trade off on battery life. I've also been thinking of adding a button to this board, so maybe you could hit the button whenever you want to change the text if you needed more responsiveness. Anyway, this thing also comes with its own 3D printed case that fits both the display and the board. Okay, now I'm actually done with this video. Like all my videos, everything in this video is open source with links in the video description if you're interested in reproducing anything shown here. There are still some rough edges with the automation scripts that connect these to other devices in your home, and let me know if anyone wants support for these in any existing frameworks like Home Assistant. Also, this tiny receiver dongle isn't particularly good, so that's another thing I'll need to upgrade in a future video. Bye!